Okay, so in this chapter what we're going to talk about is chemical bonding, and so it's building on what we did in the last chapter, which was dealing with electron configuration. And the reason why we did that whole electron configuration is because that tells us how the chemistry that's involved in reactions take place, why it happens the way it does, why CO2 is carbon dioxide, why that exists as opposed to CO3. There's no such thing. And so the chemistry that's involved all leads back to those electrons. And the electrons move around between different atoms of different compounds, and that's what makes different bonds. And so what we're going to talk about to start with is bonding, and we're going to talk about how the electrons are arranged in a compound. And then we'll talk about what it looks like in a picture. So in order to get to that, we have to do one more periodic trend. That's electronegativity. Electronegativity is the ability for an atom to pull electrons to itself from a bond. It's a tug of war. And if you look on here, fluorine's at the very top, and Fr, francium, is at the very bottom. So this has a very high value of electronegativity. Notice there is a group missing. There's no noble gases, and that's because noble gases are perfectly happy the way they are. Think back to electron configuration. They have completely filled energy levels. They are very stable, very low energy. They are perfectly happy, hunky-dory. All right. But when you look at fluorine, if you remember back in electron configuration, it's 1s2, 2s2, 2p5. It is one electron away from becoming like these noble gases with very low energy. So it really wants to attract electrons to itself, more so than any other element on the periodic table, partially because of its electron configuration and also because its atomic radius is very small. And those protons are very close to those electrons, and there's a strong attraction between them. And so fluorine, it only needs one more electron, and that one more electron, when it adds in, is going to be really close to the nucleus, so it has a very strong attraction for it. You don't need to memorize those numbers, we'll give them to you. So how do the electrons work? Well, what happens is two atoms share or exchange electrons based on their electronegativity differences, and those electrons act like glue holding the two atoms together, because every atom or element out there wants to be as low of energy as possible, as stable as possible, like the noble gases, and so that's how they do their electrons, and we'll talk about that when we get to Lewis structures. But the way those electrons are shared, holding the atoms together, is different, and that's what we're talking about when we come to bonds, bond types. Okay, there are three different kinds of types of bonds: nonpolar covalent, polar covalent, and ionic. I'm going to abbreviate this one NPC, PC, and I. Okay, and the three different kinds of chemical bonds are based on how the electrons are shared. In a nonpolar covalent bond, they are shared equally. In other words, it's a tug of war and it's a dead even tie. In a polar covalent bond, they're shared unequally. It's still tug of war, but one of the atoms is pulling the electrons to itself because it's a little bit stronger, it's a little bit more electronegative. And then in an ionic bond, it's the tug of war's over. Okay, whatever atom that was the stronger, the more electronegative atom, has pulled those electrons to itself, and it's won the tug of war. So that's what we're talking about with this. So if the atoms are equally electronegative, looking at that chart, that means the electrons spend their time in the middle, 50-50, tug of war, nonpolar covalent. Okay, perfectly shared. If the one atom is a little bit more electronegative than the other one, then the electrons spend more time by that one. This is a polar covalent bond, and it's a tug of war still. Nobody's lost, nobody's won, but somebody's winning. And the electrons are spending more time by the guy that is stronger, by the atom that is stronger. And then the last one, tug of war is over. It is 100% in one direction and 0% in the other direction. And this is an ionic. Okay, the electrons spend all their time by this guy and none of their time by that guy. And so you get a positive charge and a negative charge. Okay, so that's what that says. So difference in the way you figure this out is we're going to do something called the electronegativity difference. That means we are going to subtract. And if it is 0 exactly, it is a nonpolar covalent bond. In other words, the electrons are shared equal, 50-50, right down the road. When it's very large, you're going to get ionic, and that's where it's 0% of the time by one of the atoms and 100% of the time. So you get a positive charge and a negative charge. And in a polar covalent, you get kind of a tug-of-war. It's not 50-50, and it's not 0 and 100. It's somewhere in the middle. I mean, I hate to call it 25-75, something like that. But what you get is you get a partial positive charge and a partial negative charge. Instead of a complete positive and a complete negative, it falls in the middle somewhere. So what we're going to try and do is come up with some numbers, because people like numbers and they like to have some kind of variation. So if you subtract difference, if you subtract the electronegativities between two atoms, and it's somewhere between 0 and 0.3, it is nonpolar covalent. That usually means it's atoms of the two of the same nonmetals, so fluorine and fluorine. You could also do it for things like, I think, hydrogen and sulfur, okay, or nitrogen and oxygen are pretty close to each other. Nitrogen and, well, not really nitrogen, but like carbon and phosphorus are close to each other. So it's kind of that way. In polar covalent, it's usually two different nonmetals, so carbon and oxygen or hydrogen and oxygen, and they're very far apart from each other. And then if it's ionic, it's usually a metal, so sodium and chlorine, or magnesium and oxygen. They're very, very far apart from each other on the periodic table. So in covalent bonding, the glue that holds those two atoms together is 50-50, shared equally. In a polar covalent bond, the electrons spend a little bit more time over here. So again, I hesitate to say 25-75, it could be 40-60, but basically they spend more time over here, so it gets that partial negative charge and partial positive charge. And then in ionic, electrons are gone. The electrons spend all their time over here, so you get a completely negative charge and a completely positive charge. And that's where how you figure out what type of bond it is, really. So what we're going to do is we're going to look up the electronegativities, we're going to subtract to get a positive number, and we're going to use this. Now, there's going to be some, it's a continuum. There's going to be some gradations where you're 0.3 to 0.4. You know, if you have 0.33, well, maybe it's nonpolar covalent. If you have 0.38, maybe it's polar covalent. Okay, if you're rounding, it becomes an issue. So if you look up calcium and chlorine, if I look up calcium and chlorine, I get 3.16. That's how strong chlorine is. Calcium is 1. I get 2.16. Therefore, it's ionic. And that means the electrons completely go. You get a negative charge on this end and a positive charge on that end. If you were doing CO2, we're not really talking about the subscripts here. We're really talking about carbon and oxygen and how they are sharing the electrons that are between them, okay, in that picture. And if you look up the numbers, oxygen is 3.44 and carbon is 2.55. And when I subtract that, I get 0.89. So to me, that is a polar covalent bond. And what that means is that the electrons are spending more time by the oxygen, so it gets that partial negative and partial positive charge. That's where you get this polar covalent bond. They spend some of their time by oxygen, maybe 75% of the time by oxygen, 80% of the time, and less time by the carbon, but the carbon's putting up a good fight. It's relatively strong. Okay, so I'm going to have you guys practice on this. Okay, so look up those three, and look up the numbers, and then subtract them. So if you do nitrogen and oxygen, I get a subtraction of 0.4, which means it's just barely polar covalent. So the electrons are spending more time here, partial negative, partial positive. If I do fluorine and fluorine, 3.98 minus 3.98 is 0. That means non-polar covalent. It is dead even in between them. There is no variation at all. And then nitrogen and hydrogen, I get 0.84. And again, polar covalent. But in this case, the electrons are spending more time by the nitrogen because it's stronger than the hydrogen. So that's relatively simple. Let's do these guys. Okay, and I'm pointing these out because some of these are a little bit borderline. So if you look at H and S and you subtract, remember we're not using those subscripts. From what I can read, it looks like it's 2.58 for sulfur and 2.2 for hydrogen. So 0.38. Wow. Almost polar covalent. Well above the non-polar covalent minimum. I would probably call this polar covalent. Okay, you could call it non-polar covalent. It's kind of in that border region, but it's awfully close to being polar covalent. And so for me, I would say this gets the negative and that gets the positive. Okay, aluminum and chlorine, same idea. This is a kind of a borderline thing. You have 3.16 minus 1.61, and I make that to be 1.55. Okay, again, real close to being ionic. If you round up, I would probably call it ionic. If you wanted to call it polar covalent, it is extremely polar covalent. And to the point where the electrons are maybe spending 99% of their time by the chlorine and like 1% of the time by the aluminum. So, you know, it's a continuum. It's not hard and fast rules. And then Cl and O, and if I subtract those, I get 0.28. And again, I would call that nonpolar covalent. Okay, it's right in the, kind of in the middle. All right, so there are some generalizations you can make about the physical properties of the different kinds of compounds you have based on their bonds. If it's a nonpolar covalent, it tends to have a very low melting and freezing point. Ionic tends to be very high, and polar covalent's kind of in the middle. Nonpolar covalent generally don't dissolve in water. Ionic, yes, generally we would say they do. And then polar covalent, again, it depends. And then these guys typically are gas. These are things like carbon dioxide or helium or fluorine, things like that. These are things like salt, sodium chloride. And these are things that, you know, you can't really make a judgment call about what they're going to be, because sugar is polar covalent, and that's a solid. Water is a liquid, and it's polar covalent. And let me think something. Ammonia is a gas, and it's polar covalent. So, you know, you can't really make a judgment call here, but this one is where water is, and so that's really important. So what we're going to talk about next is we're going to talk about how to draw the pictures of what the structures look like.